Okay, my name is Francesco. I am the CEO and one of the co-founders of VAULTED. We are a ETH spin-off that commercializes the funicular floor research that we did at ETH. And for me, it was really nice to be here and reconnect with all my former colleagues. And you will be bombarded by all these Block research group things, but apparently we are doing the right thing. Of course, you know all of this. If you're here, you know that we need to care about how we design structures, I say structure because I'm a structural engineer, but how we design, how we are affecting the building industry. Of course, you know the first two, very likely. We are responsible for a lot of energy consumption and 38% of man-made CO2 emissions. But we're also responsible for a lot of the raw material extraction. 40% of the entire material harnessed from the planet is used in construction. And we build not very nicely, and we don't know what to do at the end of the lifetime, so we just dump everything into landfills. So 35% of man-made of waste is produced by the construction industry. And this is the reason why, because it's easy to design such a structure, very easy. Structural codes already fulfill all the criteria that you have to, the checkboxes and everything. But at the end of the lifetime of this structure, you don't know exactly what to do. It's a conglomerate of different materials that you have to just demolish and throw away. And the situation will not be so much better in the future because we are projected to increase our population by 1 billion people, which will require to add 190 billion square meters by 2050. So in the next, because I keep doing these presentations, and it's next 30 years, then it becomes next 25 years, and we are actually reaching these deadlines. If you don't know what it means, 190 billion square meters of new construction means that you have to build one New York City every month for the next 40 years. And this gives you the magnitude of the responsibility that we have in the future. So we have to change the way we design and build. Both are important. I say structures because I'm a structural engineer, but every part of the construction process has its own responsibility. That was the bad news. This is the good news. The good news is that it's actually quite simple. This is the equation that governs the whole problem. No? It's not a super complicated differential equation that you have to solve with, I don't know which AI. It's just a simple linear equation. So the global warming potential, so how bad our buildings, it's just a product of how much mass, so how much material we use, the quality of this material, so how bad is this material, so the embodied carbon coefficient. And then I personally add the time in it, because you can design a very sustainable low carbon structure, but then you have to change it every year or every 10 years. Then you didn't do the right job. So this is the equation. This is actually super easy. There are many different ways in which you can activate the equation, in which you can change the parameters in the equation. This is what we do at the Block Research Group. So these are the three parameters that we use when we start a new research project where we do our research. I mean, I still say we, I'm not part of the research group anymore, but I feel like a family. And so these are the three principles. Material effectiveness, which means using the right material in the right application. And I will go back to this when I will talk about concrete. Structural geometry means harnessing the power of the geometry instead of the power of the material, so over-engineered materials to achieve whatever is your objective of your structure, and the circular construction. I will go back to it. But so this is, okay, probably in this audience it's not so easy, but if I ask anyone what is your opinion about concrete, everybody would be something like this on these lines. Now, concrete is the most destructive thing in the world, 8% of CO2 emissions, and so on and so on and so on. But is it actually true? And to understand that, we have to understand the numbers. So this is the only weird stuff that I have in my presentation. But I don't know if I have a projector. No, okay. But so basically, this is a plot that shows the embodied energy and embodied carbon of different construction materials. And so the first thing you should notice is that timber is actually high up there. It's not that super eco-friendly solution that people try to advertise. The other thing that you have to see is that concrete is actually on the other spectrum. It's way down there. So it doesn't use that much energy, it doesn't use that much carbon. Even timber, carbon neutral timber uses a lot of energy. We should not forget, because now it's the time where we speak a lot about CO2 emissions, but we need to don't need to forget about energy and what we do. And another thing that you can see in this plot is that the more cement you put, the worse it gets. So concrete, unreinforced concrete is down there, stone is even lower than that, and so on and so on. So if we can achieve to use structure, they use less concrete, but also lower cement concrete, then we actually have a very good material. So this is what you can do already now without doing anything, without doing any of our super fancy research topology optimization things. You can just go from this should be almost illegal to use SEM1. You should go from SEM1 to SEM3, or whatever the industry is providing us now, and then try to lower your cement content. So already with that, you can do 70% reduction of CO2 emissions, just that. But how do you use low cement content concrete? No, how can you reduce this amount of cement? Well, these structures, the Gothic cathedral of 300, 400 years ago, that still stay there, used zero cement. They don't have any binder that keeps everything together. Why? Because they harness the power of geometry. The master builders that designed these structures, they knew that you don't need anything to bind things together if you put the material in the right location. That structure is, okay, this is it's a bit an exaggeration, but that structure is as thin, if you scale it, as an eggshell. And these designers, they could do this without any computer, without any super fancy calculation model, just by knowing simple principles of structural design. You can do something a little bit more complex than that, and this was the Armadillo Vault designed by the Block Research Group for the Biennale in 2016. This is 399 stone blocks, no binding, no reinforcement. There is nothing connecting them, no joint, no glue. They stay there just because they are in the right position. And so you can think about it that it's very easy also to demount and to reuse somewhere else, and it's done. But so just doing that, just using the material putting the material where it wants to be, just as Joris was saying before, just following the natural distribution of material, you can go with 70% concrete less and 90% less steel, because you still need the steel under to take the tension tie. And the other thing that you can do is that you can distribute stresses in a much more natural way. So in your beam, you have to design your concrete to reach the capacity of the most compressed or tension fibers. But if you distribute your material as it wants to be, and if you can center the thrust line of your loads, then you can have a uniform distributed load, so you can reduce the amount of cement, basically. You can go so low that this is possible. This is, if you see on the left, this is an arch, a bolt, that is so thin, made with a material that is actually so breakable that you can smash it in your hands. But if you put it in the right position, you can already hold the person working on it, even if it's not even complete. So you can bring these principles to a very ultimate design. So maybe if I can leave with a slide, this would be it. If you apply the principle of masonry structures, you can achieve less material, you can use better material, and your design can be much more circular. So if you go back to this equation and you start putting numbers in it, we said we can reduce 70% of the mass because we put it in the right position. We said that we can use 70% less, we have a 70% less CO2 emissions because we use CEM3 and we use lower cement content. And then we can say that these structures, they are not prone to corrosion because there is no reinforcement, they can last longer, so let's say 2. So you already now, you can use just 4.5% with this very easy calculation of the CO2 emissions that you're producing right now. Of course, it's very easy to do in small applications, and that's probably the question that was at the end of the discussion, probably. Very easy to do in this kind of small applications, and Marianne and Diederik before they are there, it's nice to see. But we need to make the change, no? We need to actually do these things in real structures, in real buildings. And I go back to this slide. This is a challenge, but this is also an opportunity. This is 190 billion of square meters of business that is there for us to grasp. Now, out of that, all the structure that we have to build, this is a mass distribution in a typical high-rise building. No? 75% of the mass of a building is in the structure. Us, it's only 5% with the furniture and everything else. So we actually build things to sustain themselves. Out of the 75%, actually out of the 100%, 41% is in the floors. So if you really want to make a change now, you should start from the thing that is most polluting, which is actually the floors. And this is because we still design things in this way. We just put material how we can, as much as possible, because also our structural codes, they don't tell us maximum limits, they just tell us minimum requirements, and this is a problem. But there are many different structural slabs in the world that you can use, but they all work in bending. And because they work in bending, they use material inefficiently, we saw it before, and they all need reinforcement, which means that they waste material, they need high-strength material, reduced lifespan because there is corrosion, there could be corrosion, and it's very hard to take them apart. So, but you can start from this, and you can sustain exactly the same load just by applying, as we said before, by placing the material where it wants to be. Of course, what I didn't say before is that load is not stable. It's not always the same. In the case of a bridge, maybe the self-load and the dead load of the superimposed load maybe are so much higher than actual live loads that you don't have to take care of it. But in the common slabs, you walking around, this is an external load that needs to be taken care of. And this is why you need to increase a little bit the material. You have to add an additional part, so you have to place the light gray part on the structure. Now, you do this in a little bit more complex way, but the principle is exactly the same, and then you have what we call a rib stiffened funicular shell, which is actually a funicular floor. Now, because of the funicular action, you have a compression dominated, because you cannot remove tension completely, element, no reinforcement, so less material, low strength material, because stress is distributed, is uniformly distributed, increased lifespan, and easier to recycle, because the materials are completely separated from each other. You have only compression and only tension. Now, we did this, and Diederik showed some examples of it. We developed this thing in 10 years, so it was a long time, but we did all the tests we had to do. We did also the test that we didn't have to do. We loaded with a bunch of nerds to show the world that actually was safe. And in the middle, Matthias, who's actually the father of this invention. And then they gave us the opportunity to test it in a real building, the same that Diederik was showing before. So that you saw basically the roof before, but inside there are actually 2 floors, real scale floors. This is the geometry of it. You can see a little bit an evolution of the shape. There is a topology optimization applied, and so on and so on and so on. But the real power of it is still the same. It's still in the vaulted geometry. And one thing I want to point out, this is the only reinforcement bar in the entire floor. It's a completely unreinforced concrete structure. That's the only thing that you have there. So if you go back and you see what we are doing now, you can see what I'm talking about. What's the change here? And this is the final product. This is a real building used right now by a robotic fabrication research group in EMPA. This is 50% less concrete, not the 70% because it was the first application and I was scared of killing someone. 80% less steel and 70% less carbon emission. The problem with this application is that it was a one-off. We had to build it in one location, and the construction of it was actually quite complicated. Yeah, you can see all the layers that you need. Just to show you, this is the bottom formwork. It's PLD plates, where you then, this is a detail of the reinforcement, so the 2 bars that I showed you before. Then you have to put something on top to create the ribs. This is also, there was another thing that we were collaborating with a building system research group, so they wanted to have a pipe for heating and cooling of the room inside, so you put it on top. You have this nice formwork, and then you pour, and then you have everything ready. Okay, so you understand that this process is not applicable to what we have to actually do, so we had to move forward. And so that's why we invented the next generation of funicular floor, what we call the Rippmann Floor System. It's a prefabricated, discretized structural element, completely unreinforced as the other one, which can be produced in a controlled environment, in a factory, delivered on site, and then assembled without any glue, without any particular joint. So these are some applications of it. This was a test that we did in our own facility, load test. We learned the lesson from the previous example, where these pipes were integrated in the floor, but this doesn't make any sense, because if you do so much effort to remove the rebars out of the floors, why do you want to put the pipes inside? It doesn't make any sense. Now everything is completely separated and integrated. But the Rippmann Floor System is a system. It's not just one solution. It can be tailored for any sort of application, from schools to car parks to office buildings, and for different types of fire safety. We did all the tests, because this was the thing that was missing during the research. Now we did all the tests in the fire chamber. Acoustic performance, we had to have real scale demonstrators and tested for airborne and impact sound transmission. And that was our first real application. And because we wanted to make our life more complicated, it was a 10.5 by 10.5 floor, so quite big, in Belgium. And this should be a video of the first. This is a mock-up that we had to build, because the client, of course, didn't trust us. Good for them. And so these are the pieces that come together. That's me assembling it, so you don't need really high complicated, super fancy construction workers. And this is the final floor. For this building, we demonstrated that we could save 7,500 cubic meters of concrete, which doesn't mean anything, but then you say that it's 1,200 beton trucks, concrete trucks, they don't have to go on site. 20 kilometers of rebars, V12 per floor. Again, it doesn't mean much, but then you demonstrate that it's from Zurich to Belgium, where this thing was, and so on and so on. So we discovered that basically we had a business opportunity. That's why we founded the company, VAULTED. And the core of the company, the vision of the company, is that we can right now make the construction industry sustainable, not more sustainable, just sustainable. And these are the things that you have to do. It's a very easy process. We saw it before also in other presentations. And we were convincing, and one of the professors in ETH, he's a designer of the tallest tower in Switzerland, came to us and said, okay, you guys want to do a competition with us? So we did a competition for this building, and we won. This is the Crea Tower in Zug. And you can see on the right the application of the floor. This is 180 floors, so 6,800 square meters. So we had to basically first beat all the competitors. The client hired another engineer to check all the other solutions and compare to ours. And they demonstrated that our solution was cost neutral. I think I heard before, because my Dutch is not that good, but I heard before about cost and how this thing can be related in real buildings. This is a demonstration that you can do something innovative without adding any cost to the building, because you use 70% less mass, so your foundations are also much cheaper. Your beams are cheaper, your columns are cheaper, and so on and so on. We had to scale up production, so we have a production factory. We had to find a way to deliver this thing properly, 180 of them. It's not easy. And then we assembled another mock-up. This was a one-to-one mock-up, 6.5 by 6.5 meters. And you can see, again, it's the same principle. You have the blocks. They are completely separated, dry jointed. You just put them together. Now, again, it's us doing it. A smarter, faster person can do it much faster, but it takes about 1.5 hours for each bay. This is the final floor. This is the underneath. You can see this is a detail for the room acoustics, because we also integrate the room acoustic in the floor. This is with the panels, and I'm pretty much done. This is what we are doing in the future. So we want to bring to you designers something to design your floors for yourself, and then we will move from this bespoke kind of design to a line that you can include in the structures directly. And that's concluded. Thank you very much.